bit of math into what we were talking about with the pictures, right? We've now got some function called f of x here, and it's on an interval from a to b. And we're going to write down what this is going to look like if we're going to try to find this area, okay? So I'm only going to draw a few rectangles because I'm not great at drawing rectangles. Maybe I'll break this up into 4. But what we have here is we've got this interval, we've got a length, b minus a, and let's say we want to break it up into n pieces, right? So we're going to break b minus a into 0, n pieces, and if I'm going to break it up, I just divide b minus a over n. That's going to be the length of each interval. Again, I'm going to, because it's easy, I'm going to make them all the same. It doesn't have to be, right? They could be different lengths, but then if you're actually going to sit down and compute it, it was kind of a pain. So in the end, we're going to take it to the number n, right? It's going to go to infinity because we're going to have an infinite number of rectangles. So that's why it doesn't really matter whether they're all the same, whether it's an equal partition or it's not an equal partition. It's just convenient to make it equal, especially if we're computing it like with finding what it is for like 5 rectangles, right? You know what? It's just easier. So this length is going to be called delta x, right? Change in x, delta x, we're going to send it, as we send n to infinity, this guy's going to go to something very, very close to 0, right? So that's the idea. For the purposes of my picture, I'm just going to break it into 4. 4 is easy, right? Okay. So this length then is the delta x, right? So, and then fine. So now how high am I going to do my rectangles? It doesn't matter. Let's see, for the purposes of my picture, I'm just going to choose the left endpoint. So I've got 4 subintervals, right? Notice that I can give them names, right? We are going to call the first one x0, the last one, in other words, the last point is xn, so this would then be x0, x1, x2, x3, and x4 in the picture because I only have 4 intervals. We start from x0 so that we end up with n. I mean, you could start from 1 and then have n plus 1, but this is just sort of the standard when you start from x0. So this point is the point x1, okay? And delta x is always the same. So if I'm going to set up, so I know that, so then I know the width of my supposed rectangles and the height, right? In this case, I've chosen the left endpoint. So I just take it out to the left. So what is this going to look like? Then my area is now going to be approximately the height of the first one, which is f of x0, delta x, plus the height of the second one, so this would be f of x1, plus f of x2, plus f of x3, right? All right, that was too much writing, okay? So I'm going to instead use summation notation, right? I'm going to say then this is going to be the sum from I equals, say, 0 to 3 of f of xi delta x, however you do it. Okay? I happen to use, I started with f of x0, so I went from 0 to 3. If I had done the right endpoint, I would have had f of x1 here and f of x4 there, so I could have done my sum from 1 to 4. If we want to be as general as possible, though, this is what we're going to do. We're going to put the area is approximately the sum, say I equals 1 to n of f, but f of what? It doesn't matter, just some point in the interval xi. So that's why your book likes to call that xi star, and this is del x. So what is xi star? Xi star is any point in the ith subinterval. Okay, and we can write down what the ith subinterval is, in fact, because the ith subinterval goes from xi minus 1 to xi. Okay, so this is our general form right here. And the only difference between left endpoint, right endpoint, midpoint, whatever, is just what point you're going to choose in each one of those subintervals. Okay? So we can then do this. Now, I will tell you what we want to do, of course, is we don't want an approximate here. We want an equal, right? Because we want to take this n off to infinity so that we get the actual part, right? So this is just called a Riemann sum when it's the sum of the rectangles, okay? But what we really want to do is take the limit of this. So I am going to erase the picture real quick. And then I'm going to take the limit. So I'm going to do area is the limit as n goes to infinity of this guy. Okay? So as n goes to infinity, delta x goes to 0, and my approximate area approaches my actual area. This is a limit. We all know sometimes limits don't exist, okay? But it turns out that under very, as long as f is continuous, not going off to infinity, right? Well, as long as f is bounded, really. But it's fine for it to be continuous at every point of the interval, if you want to put it that way. Then it's not going to go off to infinity right at the point. So it has to be continuous throughout the entire thing. That's sufficient. Okay, that's actually extra. It doesn't have to be continuous everywhere. It can jump because you can break up the interval. We'll see some examples of that later. But it has to be bounded. It can't go off to infinity. And it can't do some really wacky stuff. But anything that we're going to be using, that we're actually going to be doing anything with, won't really be that kind of issue. Okay, so let me do this. When can I do this, then? And what happens? And how do I call it an interval? What we're going to do is we're going to define this thing as an interval, okay? And what I mean is, this is a summation, right? So, but as n goes to infinity, think about, instead of being a Greek sigma, it's now going to be like a regular s, like a Roman s, but it's going to be extended. So what this is just a notation, and this is the notation, right? So this is the notation for the interval. The dx, the delta x becomes dx as n goes to infinity. Okay? Now, this is a definite integral. It's the area under the curve. Okay? Now, if this limit exists, then this integral exists, and this area is going to be, hold on a second, something went wacky with my machinery. All right, sorry about that. Then this area is going to be something that is finite. Now, let's see. So, what let's say about it? Say is that, yeah, I don't want to say about it. We're not going to really worry about this. You may have seen examples where they do this, and maybe I'll do one just for fun because it's kind of cute, right? But you can actually do this limit by explicitly putting stuff in here, figuring out what that sum is, and then taking the limit as n goes to infinity. You can do it. You probably can't do it for something that's really, really complicated, but for something fairly simple, you can actually do the limit. And you can do it multiple ways, with multiple, like whether it's the left endpoint, the right endpoint, the midpoint. This is all going to look a little bit different when you put that into that expression, but the limit, once I take n to infinity, it's going to be the same, okay? As long as your f is integrable. So what do we really need? I'm going to say this limit will exist and be the same for all choices of xi as long as f of x, we'll just say if f of x is continuous on AB, okay? Including at the endpoint. So we're not going off to infinity or anything. You're not having something which is like wildly discontinuous or anything, okay? You can relax this a little bit, but that will definitely, once it's continuous, for sure will work, okay?